Okay, so where we left off in the last lesson, we had gone from creating, we looked at creating a bar graph and different, like using averages and creating a very specific type of bar graph in order to compare qualitative data sets. So in this case, the shaft material affecting the speed of an arrow. So we use different materials. That's a qualitative change. And then down below, we looked at another experiment that we did looking at the effect of the mass of the arrow on the arrow's speed. Along the way, we looked at initially graphing all the data points, all the trials, and looking for outliers. So we can see we had an outlier right here and an outlier right there. We looked at how to calculate the average using a formula. So here's an example of a formula right here where we add up the three tables, and that's what this sum part does, and then dividing by 3 because those are the 3 trials. When we look at this data set right here for the 400 grams, the 500 grams, and the 700 grams, we can see that all those data points are really close to each other. That's really good. However, when we look at the 300 grams and the 600 grams, we've got some outliers. And remember, we talked about the fact that if I were to include these outliers in the averages, it really threw that average value off. And one of the things we looked at in the last video was how much it skewed this line of best fit. So what we're going to do today is I'm going to show you guys how you can create a good line of best fit using Excel and then extend that line if you want. And also how you can find the equation of the line and use that to make predictions. Remember, the objective to doing a scatter plot graph is that we can come up with an equation of the line so we can make hyper accurate predictions. What if my mass of my arrow was 200 grams? What if my mass was 187? What if my mass was 1342? What should be the speed of that arrow based on the testing I've done? So I'm going to click here. Remember, we can add things like axes and titles and stuff like that. And one of the things here I want to add in here is the proper title. On its average speed. Okay, really important to put that. And then, of course, this is the speed. Can anyone remember what we always need to include with the in the axes? Not just the name of the unit I'm measuring, but also the units themselves. What's the unit for speed that we're using here? Anyone know? Meters per second. That would be a really fast arrow if it was miles per second. That arrow would be super fast. So remember that we always have our independent variable across the bottom, mass of arrow, and our dependent variable is the speed, and that's along the x-axis. So one of the things that I would need to do right now is I need to change this style of chart. So if I go to design, I can change my chart type. What we did was we chose one where the lines were joined. We actually don't want that. So whenever you do a scatter plot, you're going to pick a scatter without joining the lines. All right, and you always see a preview of it, and it should look something like that. And so there we go. Now, what we can do is we can go and add a trend line. So before I click on adding a trend line, I'm going to click on this little arrow thing, and I can choose what type of trend line I want, and I'm going to go down to more options, and right now it's got me set up as a linear line. So I've got a linear line set up, and I can see my line, and it looks pretty good. If I click on my line and I right click, I can format my trend line. This pulls up a really important pop-up, which allows me to do a lot of really neat stuff really quickly. So I can choose different styles of lines, all right, that might fit. For this one, we're going to, and in grade 9, we stick a lot with linear. We'll do some labs where we'll take a look. You'll bring up the lab to me and you'll say, Mr. Pilot, this line doesn't quite fit. And then we can open up your program here, and we can take a look and play around with these. One of the things that's really neat that allows us to extrapolate is to increase the length of the line. So I'm going to forecast into the future, and I'm going to go 100 periods beyond, and I'm going to go 200 periods before. And so now my line got extended beyond just my points. So this allows me to predict using the graph, what if it was 200? What would be the speed of the arrow? What if it was 800? What would be the speed? But I want to go further than that. I also want to display the equation of the line on my chart. And what this equation does is it allows me to plug values in. So my equation on here is y equals negative 0.598x plus 117.98. So what this allows me to do is to put values in for x and y, and then I can solve for the unknown. So remember that x right here is my mass, and my y is my speed. So now that I have this equation of the line, I could throw any value in for the mass and see what the speed should be. That is the aim of science. This is why math is the language of science. Because if we can get a relationship like this, we can make hyper-accurate predictions. And that's what we would now call this our model. So this is our theory. We've got an equation here. This is a theory. It's based on evidence. It's a relationship between the speed and the mass. And we think that this relationship looks like this. Now, we may want to do more testing. We only did 3 trials. Say we extended this experiment, we did a few more masses, and we did maybe 5 more trials. We may have to tweak this model. The numbers in here may change. So we may have to change this. That's the slope of the line. It may turn out that we're not quite there yet. Or this is my y-intercept, and that may need to change. But we've got a theory here. And what we could do is we could get an arrow of, say, 200 grams, plug it into the value for the mass, see what we should get for its speed, and then test it out. And that's what we do in science. We ask a question, we make an observation, we ask a question, we come up with a guess, a hypothesis, we design an experiment, we collect the data, we analyze the data, and if we've collected enough good data and we don't have a lot of outliers, if our data is nice and tight, then we probably have a good model that we can use. And then we can test that model to see if it actually works. Let's take a 200 gram arrow and let's shoot it 3 or 4 times, and we should get the value that if we crunch punch the number in for 200 for the mass, we should get the speed around what we predicted with the model. That's why we do all this stuff. All right? So this will be some of the things that we're working towards in the course.